This video explains the source-coupled VCO working principle. It is a particular kind of voltage-controlled oscillator sometimes used in phase-locked loop for its low-power dissipation. The general idea of a voltage-controlled oscillator is modulating the output frequency by modulating the input voltage. By applying the input voltage V in VCO, we generate an ID current through the MOSFET M5 and M6, which behave as constant current sources sinking a current ID. MOSFET M3 and M4 operate in saturation mode and pull the outputs up to VDD minus V threshold. MOSFET M1 and M2 act as switches. So let's say that M2 is on and M1 is off. In this case, the voltage drop on M2 is close to zero if we properly size the MOSFET to act as a switch, and the voltage on the output is pulled down to VDD minus 2V threshold, which is the voltage on the drain of M6-2. In this situation, a current of 2ID passes through M4 and M2 because M1 is off, but M5 keeps sinking ID from the capacitor. The current ID charges the capacitor, and because the drain of M6 is kept to VDD minus 2 threshold by M2, the charging of the capacitor pulls down the voltage of the drain of M5. The voltage in the drain of M5 keeps lowering till the moment it reaches VDD minus 3V threshold. In this moment, between gate and source of M1, there is V threshold, so M1 switches on, causing an immediate voltage drop in the drain of M1 or output bar, which reaches VDD minus 2 threshold, switching off M2. There is also an immediate voltage increase in the drain of M5, which passes from VDD minus 3V threshold to VDD minus 2V threshold, causing the output to rise the voltage to VDD minus V threshold. This sudden increase of voltage in the drain of M5 doesn't give to the capacitor time to charge, and it lets pass the voltage increase to the other end of the capacitor, which rises from VDD minus 2V threshold to VDD minus 1V threshold. So, calling the end of the capacitor point X and Y, we have this voltage behavior on the output and on the ends of the capacitor. We see that when M2 is on and M1 is off, the voltage on the output is VDD minus 2V threshold, the same of point Y, which is kept to this voltage while the capacitor is charging, pulling down the voltage in point X. When the voltage in point X reaches VDD minus 3V threshold, M1 switches on and M2 switches off. The voltage on both plates of the capacitor immediately increase of a V threshold, as well as the voltage on the output, which becomes VDD minus V threshold. Things go on in this way, and circuit output oscillates between VDD minus 2V threshold and VDD minus 1V threshold. So you need to size carefully all the MOSFET and defining the V threshold carefully. M1 and M2 used as switches need a low on resistance, so they should be larger in comparison to M3 and M4. Moreover, the oscillation range is just of 1 V threshold, so you need an inverter on the output to restore the logical values.
Seeing the general behavior of the circuit, we see the oscillation frequency. We noted that the voltage drop on the capacitor is 2 times the threshold voltage, so charging the capacitor with constant current ID takes this time here. The oscillation frequency is this because in a period we have to charge the capacitor twice, one in a direction and one in the other. So we related the frequency to the constant current ID, but this current is related to the input voltage V in VCO from this relation because M5 and M6 operate mostly in saturation region. So in the end, changing the input voltage VGS or V in VCO makes the oscillation frequency change. So in a process of 0.80 micrometer, we could build a source-coupled oscillator which can vary from 300 MHz to 450 MHz, and the input voltage swings from 1.4 to 1.8 volts. Below 1.4 volts we have some nonlinear effect, so this kind of VCO has a low range of oscillation and the disadvantage of having a large capacitance, so you need more area. Here a comparison between the source-coupled VCO and the current-starved VCO, which we saw in previous video, and I leave a link in the description about it. Here the voltage-frequency relation, where we see that the current-starved has a better frequency range. We see the performances of the current-starved are generally better in tuning range and area. The source-coupled VCO is superior only for the power consumption. Please leave me a comment and let me know if you liked this video. Make sure you put the thumb up, click the notification bell and subscribe to my channel.